1.1.2, calculating the general lighting load. The general lighting load includes general use receptacles of 20 amps or less, including bathrooms and garages, outdoor receptacles, and lighting outlets in the dwelling. Use the NEC and your calculation worksheet to calculate the general lighting load for your residence. So here it says, using the measurements from figure 3, multiply the length of the building times the width to find the total area. And they said it was 33 feet by 48 feet. That's 1,584 square feet. Note if a building is under construction, you can determine the dimensions by calculating the building's working drawings. Calculate the area not used for living space. NEC section 220.5C requires that areas for each floor be computed from the outside dimensions, which you did in step 1. When you calculate lighting loads for residences, the code requires you to omit open porches or unused, unfinished spaces that are not adaptable for future use. So look back at figure 3. You can see there's an open carport, not part of the living space. You need to find the area of the carport so you can subtract it from the total area of the building. So again, this is what they're talking about. Why did you do that to me? Here's the carport, 19 foot 6 inches by 12 feet. There's your carport. Okay. So that ended up to be 234 square feet. When we subtract 234 square feet from 1,584 square feet, we end up with a net total of 1,350 square feet of living space. So they took that 1,350 square feet of living space times 3 volt amps per square foot as per 220.41, and they got 4,050 volt amps. Boxes 1 and 2 of calculation worksheet for residential requirements. 4,050 volt amps. 1.1.3, calculating the small appliance load in the kitchen. Small appliance load includes circuits that feed the required kitchen area receptacles, as well as dining rooms, breakfast nooks, pantries, as required in NEC section 210.52b. So here's the countertop space in the kitchen and any receptacles in here. Not the garbage disposal, not the dishwasher, not the range, but the general purpose receptacles, plugging in a blender or a toaster or a mixer, any of those. That's what we're talking about. It says, look back at the floor plan. It says, based on the NEC section 210.11C1, at least 2 120 volt, 20 amp small appliance branch circuits must be installed for the small appliance loads in each kitchen area of a dwelling. If you have 2 kitchens, you have to supply a minimum of 4 small appliance branch circuits, 2 per kitchen. Therefore, you need to install a minimum of 2 small appliance branch circuits. Are you allowed to put more than 2? Yeah, you can put as many as you want. Enter the number 2 in box 3 of the calculation worksheet. To calculate the small appliance load according to NEC section 220.52a, it shall be computed at 1,500 volt amps. Therefore, multiply the number of small appliance branch circuits by 1,500 volt amps. That equals 3,000 volt amps. Enter 3,000 in box 4 of the worksheet. 1.1.4, calculating the laundry circuit load. As shown in figure 8, the laundry circuit load includes electrical laundry equipment, such as a washer. Use the following steps to compute the laundry circuit load for your dwelling. Now, by code, you have to supply a laundry branch circuit in each dwelling unit. You have to have a means of sanitary washing machine for your clothes, and some means of cooking, a range. Those are the 3 things that comprise a dwelling unit. You have to have sanitary facilities, somehow to wash your clothes, and some way to cook a meal. You don't have to have a dryer. It's not an obligation. It's not mandatory. You can have a clothesline in your backyard and hang your clothes out on the clothesline and dry them that way. You have to have a laundry circuit for the washing machine, but you don't have to have a dryer. So here's their one circuit for the GFCI for the washing machine. And I'm going to read that section, but I believe that this circuit for the washing machine cannot feed any other receptacles. I think these should be on a separate circuit from the washing machine. I don't know if I'm going to read that and make sure that it's true. Laundry circuits 1500 volt amps per NEC section 210.11C2 and NEC section 220.52B. Dryer requires GFCI protection, NEC section 210.8A11. Here's a highlight. It says, based on NEC section 210.11C2, which requires one dedicated 20 amp branch circuit for the exclusive use of the laundry area, you need to install one laundry circuit. That means nothing else can use that circuit. That's kind of what I thought too. I'm not sure if you're allowed to put these receptacles. That would probably be up to your authority having jurisdiction in your area. I always interpreted that as meaning you can't put other receptacles on that circuit. It's a dedicated circuit. Enter the number 1 in box 5 of the worksheet, similar to the load for small appliances. Here's a highlight. It says NEC section 220.52B states that the load for a laundry circuit shall be calculated at 1500 volt amps. Therefore, multiply the number of circuits in step 1 or from step 1 by 1500 volt amps to get the laundry circuit load. 1 times 1500 volt amps is 1500 volt amps. Enter 1500 in box 6 of the worksheet. All right. 1.1.5, calculating the lighting demand load. At this point, you have the information you need to calculate the subtotal for the general lighting and appliance loads. Simply add the values of boxes 2, 4, and 6 and enter the total in box 7. Therefore, the final values found are as follows. So 4,550 plus 3,000 plus 1,500 is 8,550. You might wonder why this is the subtotal and not the total of the general lighting load. The NEC recognizes that it's very unlikely that you'll ever use all residential electrical outlets at the same time. For that reason, you can use a diversity or demand factor in your calculations. A demand factor is the maximum amount of volt amp load you expect at any given time, compared to the total connected load of the circuit. So here's a highlight. NEC Table 220.45 to determine the total demand of your dwelling. Here's the highlight. The table shows the demand factor of the first 3,000 volt amps shall be calculated at 100%. Loads from 3,001 volt amps to 120,000 volt amps should be calculated at 35%, and loads over 120,000 volt amps should be calculated at 25%. Therefore, calculate the first 3,000 volt amps at 100%, and the rest, which I think was 5550, at 35%. So there's 3,000 volt amps at 100%, and then 5,550 volt amps times 35% is 1,943 volt amps. So, and then those two are added together to get a net total of 4,943 volt amps. 1.1.6, calculating the fixed appliance load. This is different than the small appliance load. The small appliance load are the countertops in the kitchen, things that you can pick up and carry across the room. A blender, a mixer, a toaster, even a toaster oven. Those are all small appliances. Fixed appliances are dishwasher, water heater, ice maker. These are things you're not generally going to just pick up and carry away. The next section of your calculation worksheet is for finding the required load for fixed appliances, such as a dishwasher or hot water tank. So according to NEC section 220.53, if the fixed appliance has a nameplate rating, you should use that as the load. If the fixed appliance has a motor, Look up the NEC full load current in table 430.248 and multiply it by 120 volts. NEC table 430.248 lists the full load current for single phase alternating current motors running at usual speeds and motors with normal torque characteristics. So, using table 430.248, include the NEC full load current for the garbage disposal and the furnace blower. So, the disposal is 9.8 amps times 120 volts, 1,176 volt amps. The gas furnace blower of 3rd horsepower is 7.2 amps times 120 volts is 864 volt amps. So, now, did they tell us, where did they tell us that we're allowed to use 75%? All right. I may have missed it, maybe they haven't told us yet, but here are the 4 of them. So 4,500 volt amps for the water heater, 1,500 volt amps for the dishwasher, 1,176 for the disposal, and 864 for the gas furnace blower. So we add all of those together, we get 8,040 volt amps. Now, here's the highlight. According to NEC section 22053, you should apply a demand factor of 75% for 4 or more fixed appliances, as long as they're not electric heating, air conditioning, cooking, or clothes dryers. Those items are considered other loads and will be included in other loads section, which you'll calculate next. So that's 8,040 volt amps times 75%, 6,030. That's what we'll put in this box number 23. Very good. Here are those other loads, 1.1.7. Bottom section of the calculation worksheet is for calculating all other loads you need for a residence, as referenced in NEC section 220.14. Under other loads, list the electric range and the electric dryer. You should also include any other loads in the dwelling, such as electric heat and air conditioning. So, first determine and list the demand loads for the electric range. Says refer to section 220.55 for information on calculating the load of the electric range and other cooking appliances. Demand factors depend on the number of each type of appliance. For example, for a single range rated between 8.75 kVA and 12 kVA, NEC section 220.55 permits demand of 8 kVA. Dwelling has one range rated at 12 kVA, meaning the demand load is 8 kVA. So put that in, 8,000 volts. Now, where did we put the power? Where is it? Okay. And the electric dryer. Here it is. Refer to NEC section 220.54 for information on calculating the load of electric dryers. Like ranges, the demand factor depends on the number and type of appliances. For 1 to 4 electric dryers, 220.54 lists the demand factor as 100%. NEC table 220.54 instructs you to use 5,000 volt amps or the load on the nameplate, whichever is greater. Your dryer is rated 5,500 kVA, 5.5 kVA with a demand factor of 100% per table 220.54. Converted from kVA, the demand load would be 5,500 volt amps. So we enter that in box 27, 5,500. To get the correct value of all other loads, add 25% of the largest motor in the dwelling. NEC section 430.17 explains how to select the highest rated motor. And for us, that was the blower motor. I'm sorry, the disposal was the half horsepower. That disposal was 1,176. We're going to take 25% of that and add 294 volt amps for the largest motor load in the residence. Calculate the total volt amp demand. To get the minimum demand of the phase conductors, add the totals from general lighting load, fixed appliance loads, and other loads worksheet sections. So add all of those together. We end up with 6,000, well, they ended up with 24,767. 24,767. These are the things they added. Total demand for general lighting and small appliance branch circuit and laundry load, the fixed appliances, and the other loads. They added all of those together and got 24,767. Required service size. You're not quite finished with the calculation worksheet. You still need to calculate the required service size. So you know the total load for the sample dwelling is 24,767 volt amps. The conventional electrical service for residences uses 120 240 3-wire single phase. Services are sized in amps. You calculate amps by dividing the total volt amps by the highest volts in the service. So 24,767 divided by 240 volts is 103 amps. The overcurrent rating for the service entrance conductor must be a minimum of 110 amps, which is a standard rating for overcurrent protection. You can find those in 240.6 if you don't know what the standard sizes are. Look it up in 240.6 in the code. 103 amps result from step 1 does not meet this minimum requirement. Therefore, 110 amps would be used on your worksheet. However, in actual installations, since 110 amps is not a typical trade size for a load center, you may use the more common rating of 125 amps as the size of your service. Here's a highlight. Note that if the demand of the sample dwelling unit had a load of less than 100 amps, NEC section 230.79C, which is services, would have required a minimum rating of 100 amps for this single-family dwelling service disconnect. Very good. You have to go by the minimum allowed for a one-family dwelling. 1.2.0, applying in demand factors. Recall that a demand factor is the maximum amount of volt amp load that you can expect at any given time compared to the total connected load of the circuit. You calculate the maximum demand of a feeder circuit by multiplying the connected load by the demand factor. Table 1 lists the NEC sections where you can find the rules for applying demand factors to specific types of loads. So receptacle load outlets, 220/14I. Lighting loads, 220.42A. And that was that first 3,000 volt amps at 100%. Dryer load, NEC Table 220/54. Range loads, NEC Table 220.55. Dwelling unit loads, 220.82. Existing dwelling unit loads, 220.83. Multifamily dwelling loads, 220.84. Demand factors for electric ranges. The method for calculating the demand factor for electric ranges depends on whether you're using NEC Article 220 Part 3 or Part 4 and the type of dwelling. Use Table 2 to find the specific code you need to know. So, Article 220 Part 3 is NEC Section 220/55, but Part 4 is optional feeder and service load calculations. They've got an entire optional method that you can use. That would be NEC Section 220.82 for dwelling units. And NEC Article 220 Part 4, optional feeder and service load calculations for existing dwelling units is 220.83. Calculating demand factors for the neutral conductor. So your neutral, anything over 200 amps, you're allowed to derate to 75% on that neutral. So if there was a load of 250 amps, anything over 200 amps, you could derate it to 70% in order to calculate the neutral. So we would end up with 200 amps plus 235 amps. I think 235 amps. 70% of 50 amps, I think, is 35 amps. So we'd end up with 235 on the neutral. instead of the 250 on the ungrounded conductors. Go back to your calculation worksheet. You can see that you still need to fill in information in the neutral column on the right. In most cases, the neutral conductor of an electrical system carries the difference in current of the phase conductors. If you have a single-phase feeder circuit with one phase conductor carrying 50 amps and the other carrying 40 amps, the neutral conductor will carry 10 amps. It carries the imbalance. It carries the difference between the two. Because the neutral almost never carries as much current as the phase conductors, NEC section 22061 allows you to apply a demand factor. 22061B1 states that one of two situations where you are permitted to apply a demand factor to a feeder or service neutral load is when the service or feeder is supplying household electric appliances, where the maximum unbalanced load has been determined in accordance with Table 22055 for ranges and 22054 for dryers. So you're allowed to go 70% on the neutral for dryers, and you're allowed to go 70% on the neutral for ranges, and also anything over 200 amps for the main, you're allowed to go to 70%. So household electric ranges, wall-mounted ovens, counter-mounted cooking units, and dryers, 22061B1. Let's see here. Now let's size the neutral conductor. The neutral conductor in a 3-wire single-phase service carries only the imbalanced load between the two ungrounded wires and legs. Since there are several 240-volt loads in the previous calculations, these 240-volt loads will be balanced and therefore reduce the load on the service neutral conductor. Follow the steps below to size the neutral conductor. Calculate the neutral conductor size for the net general lighting and small appliance loads and enter it in box 13 of the calculation worksheet. It's the same as the value in box 12, which is 4,943 amps. All of those are 120 amp 20 volt loads. So that neutral is going to carry any of the imbalance between the two. And you may only have, it's worst case scenario, but you may only have one leg carrying all of the amperage. So it has to be the same as the ungrounded conductor. And this should have had a V. It should be 4,943 volt amps, not amps. That's a lot of amps for residents. They're the same value because the small appliance loads for the kitchen and laundry area are 120 volt circuits that have a grounded conductor, which is the neutral. Calculate the neutral conductor size for the fixed appliance loads by totaling the 120 volt fixed appliance loads. So if you have 3 or fewer appliances, enter the value in box 22. If you have 4 or more appliances, enter the box in 24. In your sample dwelling, the hot water tank is strictly 240 with no 120 volt load. So you do not have to include it in the neutral conductor calculation. That leaves 3 fixed appliances on the neutral conductor operating at 120 volts. Dishwasher at 1500 volt amps, the disposal at 1176, and the blower at 864. So those 3 added together is 3540, and that's 100%. So you put that in box 22, 3,540 volt amps. The electric range and clothes dryer both have 120 and 240 volt loads. 22061B states that you shall compute the neutral load at 70% of the demand for the phase conductors. So 8,000 volt amps for the range times 70% is 5,600 volt amps, and 5,500 volt amps for the dryer times 70% is 3,850 volt amps. Calculate the total neutral demand and enter it in box 34. So here are all of the neutral demands, and you add them all up. 8,227 volt amps divided by 240 volts is 76 amps. Box 36. Enter the gauge according to NEC section 110.14C1. If the terminals are marked as suitable for use with conductors rated at 75 degrees Celsius, the minimum size of the neutral would be a number 4 gauge copper or number 2 gauge aluminum. Based on table 25066, the grounding electrode conductor should be a number 8 gauge. If the terminals are not marked, refer to the following column of NEC section 310.16. If the amperage is less than or equal to 100 amps, use the 60 degrees Celsius column. If the amperage is over 100 amps, use the 75 degrees Celsius column. Very good. So here they are. They put all of these values in for the neutral. 4,943, 3,540, 5,600, 3,850, and 294. They added all of those up together, 8,227 volt amps, came up with 76 amps. So you need a number 8 for the neutral conductor, overcurrent device, and minimum size grounding electrode conductor. The grounding electrode conductor has to be a minimum of number 8. 31012, this is a number 2 gauge and a number 4 for the neutral. The grounding electrode conductor can be a number 8. NEC section 310.12 gives special consideration for sizing 12240 or 12208 single-phase residential services and feeders. It states that you should size conductors using NEC Table 310.12a. Size the neutral conductor according to NEC section 310.12 or NEC section Table 310.16 using the appropriate column for the markings on the service equipment. Well, it's less than 100 amps, 76 amps, so we're going to use the first column. We'll use the 60 degrees Celsius column to size our neutral, okay? To size the neutral 4 gauge. Let's take a look. Let's see if we can find that. Let's go to 310.16. If I go back to my table of contents, is that right? I go to 310, there you go, 310.16, page 177. Let's find page 177. This thing does something crazy. All right. There, let me go here. Which one is this here? Here's article 310, 310.4, 310.15b. Here's 310.16. So we need a 75 amp. See, they're saying number 4. I'd say we need a number 3, neutral, good for 85 amps. I'm wondering if they used the 75 degrees Celsius column. Well, the ungrounded conductors are over 100 amps, so maybe they used the 75 degrees Celsius column. They said 85 amps, so number 4. All right, I'll buy that. I'll buy that. All right. And grounding electrode conductor. Yeah, let's take a look at the grounding electrode conductor for number, let's see here, what size? Number 2 gauge. So number 2, we didn't use table 310.16. We used 310.15. Where is it here? What am I looking for? 310.15. No, it's 310.4. I want that. Where's 310.15? Well, all right. Okay, here it is. Table 310.12a. Table 310 or 310.12, single-family dwelling services and feeders for a service. They're telling us that we can use a slightly smaller conductor. I was telling you about this before, the 83%. It says for a service rated 100 amps through 400 amps, the service conductor supplying the entire load associated with one family dwelling, or the service conductor supplying an entire load associated with an individual dwelling unit in a 2-family or multifamily dwelling, shall be permitted to have an ampacity of not less than 83% of the service rating. If no adjustment or correction factors are required, Table 310.12a shall be permitted to be used. So here is Table 310.12a, single-family dwelling services and feeders. And they said they were going to use a 125 amp service, so they're going to put a number 2 copper. Number 2 copper. And that's different than what they were saying before 310.16. If we had gone 125 amp, we would have had to use a number 1. They're saying we can use a number 2 for that 125 amp. So, and then again, they're using number 4 for the neutral. All right, very good. Sizing the load center. After you complete the calculation for the electric service load, it's time to figure out the load center needed to support the residence. A load center is a type of panel board located at the service entrance of a residential electrical installation. It distributes the electricity that comes from the service, the source to the branch circuits, such as lighting and small appliance. So what we need to do is figure out how many of these we need, and then get an adequate panel that has room for future expansion and also has a main disconnect large enough for what we need. They said 125 amp. There again, it's just my opinion, but if it's 125 amp, I wouldn't put anything less than 150, and I would probably go to 200 in any house I was doing. Here is a highlight step 1. It says, start with a general lighting load. According to box 2 on your worksheet, that number is 4,050 volt amps. Divide 4,050 volt amps by 120 volts to find the amperage. So 4,050 volt amps divided by 120 volts is 33.75 amps. Now, we're going to want to divide that either by 15 or 20 amps. It says for your sample residence, you'll use 3 15 amp circuits. And what we want to do is understand, first of all, that lighting is a continuous load. So when I take 4,050 and divide it by 120 volts, we get 33.75 amps. I'm going to multiply that times 1.25 for a continuous load and get 42.1875. So that's 3 15 amp circuits would give me 45 amps. So that'll work. I can put them on 3 15 amp circuits. If I was doing a 20 amp circuit, I would multiply it times 1.25 to find out how many I would need also. In other words, if I tried to use 20 amp circuits, I'd still need 3 of them, more than 40 amps. So I'd have to use 3 of them, 42.1875. So we might as well go ahead and use 15 amp. All right. Recall that NEC section 210.11C1 states that you shall have 2 120 volt 20 amp small appliance branch circuits for each kitchen area. And NEC section 210.11C2 says you must have 1 20 amp branch circuit for the laundry area. So that's 3 right there. That's 3 for the general lighting load, and 2 for the small appliance branch circuits, and 1 for the laundry loads. That's 6 20 amp circuits so far. So in addition to the lighting circuits, you need 2 20 amp small appliance circuits for the small appliance branch circuits and 1 20 amp circuit for the laundry branch circuit, as shown in figure 22. So there's your 6 20 amp, or they're saying 15 amp for the lighting loads and 20 amp for the small appliance branch circuits and 120 amp for the laundry load circuit. All right. Now determine how much space you need in the load center for the remaining loads. Each 240 volt load requires 2 spaces. Each 120 volt load requires 1 space. So NEC section 210.11C3 requires 1 separate 20 amp branch circuit for each bathroom receptacle. That's one of those. Each bathroom branch circuit is not individually part of your worksheet because it's part of the calculation for the general lighting load. However, you need space for it in the load center. So, and then it goes on to say, okay, the hot water heater is 2 spaces, dishwashers 1 space, disposals 1 space, electric range is 2 spaces, electric dryer is 2 spaces, and then the blower motor for the AC is 1 space. Some existing installations, you might find a 2-pole fuse block containing 2 cartridge fuses being used to feed a residential electrical range, although they are uncommon. Calculate the load center size by adding the spaces you need for general lighting, small appliance, laundry loads to those you need for the fixed appliance loads, other loads, and bathroom branch circuits to get a total load center size. So we need 16 spaces. You need at least a 16 space load center to handle all your circuits. And again, leave a lot of spares. So here, it looks to me like they're getting a minimum of a 30 circuit panel, which is nice. I think 42 is the maximum you can get. Okay, hold on. 1.3.1 using ground fault circuit interrupters. The overcurrent protection installed on services, feeders, and branch circuits protect only the conductors and equipment. To protect people, the National Electrical Code requires that you install a ground fault circuit interrupter for receptacle outlets and, or other equipment in any location, well, it says many locations and occupancies, but any location dealing with water. GFCI is a safety device you install in place of a regular outlet. It shuts off the circuit if it detects a difference between the hot and neutral wires. An example, the phase conductor and the grounded circuit current carrying conductors. A GFCI is a device that protects personnel by de-energizing the circuit when a ground fault current exceeds the values established for a Class A device, which is 6 milliamps. According to NEC Section 210.8A, all 125 volt and 250 volt receptacles in a dwelling that require GFCI protection shall be readily accessible. In addition to the location in Figure 24, the rule applies to accessory buildings with a floor at or below grade level, such as sheds, crawl spaces, and boathouses. So we need one in the utility for the the washer, one for the disposals GFCI, any receptacles, the small appliance branch circuits are GFCI, any receptacles in the carport are GFCI, any receptacles in the bathroom are GFCI. So bathrooms, garages, outdoors, basements, kitchens. Oh, that's what they mean by this. If there was a basement, any receptacles in the basement would have to be GFCI. Kitchens, sinks, bathtubs or shower stalls, and laundry areas. What they mean by sinks is sometimes you have a sink that's not in the kitchen. You might have a slop sink in the utility room. If you have a receptacle within 6 feet of that slop sink, it has to be GFCI protected. And any receptacles on the outside of the house, by code, you have to have a minimum of 2, one in the front yard and one in the backyard. And they have to be GFCI protected. So, GFCI requirements provide GFCI protection for 15 and 20 amp, 125 volt to 250 volt receptacles and dwellings, 60 amps and less. 210.8A. Requirements to provide GFCI protection at temporary construction sites, Article 590. Requirements to provide GFCI protection for special equipment such as elevators, Article 620. Requirements to provide GFCI protection for special equipment such as swimming pools, hot tubs, and hydro massage, Article 680. Here's a highlight. It says single pole units, 15, 20, 25, 30, 50, and 60 amps. At 120 volts AC, they all have to be GFCI for a construction site. Any temporary power for a construction site basically needs to be GFCI. They're telling you how a GFCI works, ground fault circuit interrupter. Basically, it has a current transformer. The hot conductor and the neutral conductor go through that current transformer, and when their opposing magnetic fields cancel each other out, this current transformer reads a reading of 0 amps. When there's a difference of even 6/1000ths of an amp, 6 milliamps difference between what's going out and coming back, then this solid state circuitry will trip the circuit, open it, and it'll disconnect all power. Okay. Here they're showing you, here's a ground fault. There's some trickle current going on the ground wire. And if that happens, it'll trip. And here's a 240 volt, 2-pole GFCI breaker sensor disconnects both hot legs A and B when tripped. 2-pole GFCI breaker continuously monitors the current balance between the two hot conductors and the neutral conductor. Remember, that neutral carries the imbalance. So if you have the same current going out on the hot conductor and coming back on the phase B, A phase and B phase, then it's balanced and everything's fine. Or if you have more amperage going on A phase than B phase, but the rest is coming back on the neutral conductor, again, everything is balanced and it won't trip. So they're saying there's 10 amps on A phase and only 5 amps on B phase. There will be 5 amps on C phase. And if that's the case, then the GFCI sees a net reading of 0 and it doesn't trip. All right. Let me see if I have any highlights. I'll leave you with this. But for hot tubs, spas, things like that, you use a 2-pole GFCI. You have to feed it with ground fault circuit interrupter for a hot tub or a spa. All right. Let's see. Okay. Well, on this, I think what they're trying to get across to you is that you have a line and a load side. The line side takes the hot and the neutral from the panel. The load side goes out to other receptacles. So these 3 receptacles can be protected by this GFCI if they're wired on the load side of the GFCI. And on the back of the GFCI, it physically says line and load. Line is the incoming line from the hot, from the circuit breaker, and load is going out to other receptacles you want to protect with GFCI. Okay. Arc fault. Another safety device is an arc fault circuit interrupter. An AFCI breaks a circuit when it detects electric arcs. NEC section 210.12b states that all branch circuits that supply the lighting and general purpose receptacles for or devices in dwelling unit kitchens, family rooms, dining rooms, living rooms, parlors, libraries, dens, bedrooms, sunrooms, recreation rooms, closets, hallways, laundry areas, or similar rooms or areas. We talked about that before. As well as all circuit extensions or modifications shall have AFCI protection. So, or similar rooms or areas means every room in the house. Every room in the house. They said kitchens, family rooms, dining rooms, living rooms, parlors, libraries, dens. They even said bedrooms, sunrooms, recreation rooms, closets, hallways, laundry areas, or similar rooms. Have to have arc fault protection. Surge protection, voltage spikes can damage electrical devices. NEC section 230.67a requires that all dwelling unit services be provided with a surge protection device. NEC section 230.67b requires the surge protection device be located in the service equipment or immediately adjacent to it. Very good. All right, well, here's your section 1 review. Small residence has a floor area of 900 square feet. What's the general lighting load? The dwelling has 2 kitchen areas. The total small appliance branch circuits required would be how many? And according to table 22054, a household with 2 dryers has a demand factor of a lighting load of 2,700 volt amps at 120 volts has an amperage of, just divide 2,700 by 120. All right, very good. I'll see you on the next video.